Cool. So, good morning, everybody. My name's Rijndael. I work at Taproot Wizards. We've been doing things on Metaprotocols for the last couple of years now, mostly putting large or non-standard JPEGs on chain, but we've also done a lot of work on token protocols, on fungibles, designing new token protocols, using covenants, lots of other things. Before that, I spent some time working on Bitcoin self-custody, and I spent about a decade and a half working on really large-scale distributed systems, infrastructure management, and applying security and cryptography to make really large distributed systems work. I've been looking at what's been happening in Metaprotocols and drawing on past experience, and I think that there's a tool that isn't really explored a lot in Metaprotocols, and that's policy signers. This is not the right tool for every situation. This isn't going to solve all of your problems. In fact, in some cases, this might create more problems for you. But I'm hoping that maybe after this talk, you have kind of another tool in the toolbox. It'll sit in the back of your mind, and then maybe someday, one day, you'll be working on a protocol or a product, and maybe this will get you out of a jam. So first talk of the day, and I kind of need to level set a little bit on what is a Bitcoin meta protocol. This is my opining the philosophy at you for a minute. Bitcoin has a set of consensus rules. So things like when you make a Bitcoin transaction, all of the scripts on the input side have to have a witness that satisfies the script. You can't create more output values than you have input values. If any transaction ends up in a block that violates Bitcoin consensus rules, Bitcoin nodes will reject that block. Miners don't get paid if you reject their block, so these transactions end up not going into blocks. Bitcoin nodes enforce Bitcoin consensus. Meta protocols are a set of rules that go on top of Bitcoin consensus that are not enforced by full nodes, but are still really useful to things like wallets and indexers and marketplaces. Some examples of this, I think everybody's probably familiar with ordinals at this point. Ordinals add a new set of rules on top of Bitcoin. We have rules for how sats are numbered. We say when a block is mined, we take the block subsidy and we just number the sats. When we make a transaction, all of the numbers kind of carry from the input side to the output side. BRC20s add rules on top of inscriptions and say, okay, now we're going to add fungible token semantics. There's many more. I think there's a Taproot Assets talk later today. But we've been able to put new rules on top of Bitcoin. And then one of the lessons that we've learned as a community over and over again is that even though these aren't enforced by L1 consensus, we can still build really useful and very valuable economies on top of these. Because if my wallet and your wallet both agree on where an asset is, we can do trade. There's some good and some bad with this. It's a real double-edged sword thing. The great thing about meta protocols is that we don't have to change Bitcoin. It doesn't take Bitcoin consensus. The bad news is that you don't get Bitcoin consensus. So some things that we can do with meta protocols trustlessly, we can do something like a limit sell order with an inscription or with some fungible tokens. I can make a PSBT that says I will sell a specific ordinal for 100 Bitcoin. I can broadcast this to the world. Somebody can attach an input paying the right amount of Bitcoin, and it works. You can do the same thing with fungibles, and this really works anywhere that PSBTs work. These things do the heavy lifting of the entire ordinals and runes economy at this point. So if you kind of imagine this, we've got this situation where I've got this green input here. This is 100 or 10,000 units of a foo fungible token. And I stick this in a PSBT, I sign over this input, and I say, anyone is allowed to spend this as long as they provide 1 Bitcoin as the other input of this transaction. So, Bob comes along and he provides a 1 Bitcoin input to this PSBT. It makes the whole transaction valid. 1 Bitcoin ends up going to the seller, and 10,000 units of the foo token go to the buyer. And this is the way that we can list ordinals for sale. We can do batches of runes for sale. The problem is we can't do this the other way. We can't say, here's 1 Bitcoin, and anybody can claim this Bitcoin if they provide 10,000 units of a foo token. And the reason why this doesn't work is because we cannot validate these tokens in this Bitcoin script, right? If you think about, does everybody know what runes are? If I say runes, is everybody familiar? Okay, great. So runes are, a fungible token protocol on Bitcoin, and they have their own rules. Those rules are not validated by Bitcoin consensus. So if I have 10 units of some rune, and I go to send Jeremy 10 of them, and I go to send myself 10 of them, I'm trying to spend 20, but I only had 10. That can be a valid L1 Bitcoin transaction, but it's an invalid runes transaction, and it burns those coins. What if I construct this transaction and 50 transactions ago in the lineage of this input, I burned those tokens? There's no way for the script in this one Bitcoin input to validate that those runes are good. In fact, it's actually worse than that with things like runes in BRC20 because you need the whole transitive history of those tokens in order to prove their validity. And if you do an open mint, which is the way that we do a lot of token distribution on Bitcoin, you actually need full block data to know that your mint was valid and that the token wasn't minted out before you got yours. So we really can't encumber layer 1 Bitcoin with rules that depend on the state of Metaprotocols because we don't know how to validate those Metaprotocols in Bitcoin. What this ends up meaning from an application perspective or from a capability perspective is you can't really do limit buys. You can't say, I have 1 Bitcoin, I will buy any amount of food that you give me as long as it's at a rate. This is actually the reason why we can't do real AMMs on L1 for something like runes. This is the reason why there's no resting liquidity on chain, why it's so hard to get rid of your bags. We also can't do things like DAO-style pools where you say, I've got a bunch of Bitcoin and I make a 10K ordinal collection, and all of my ordinal holders can kind of vote on what to do with the Bitcoin. You have to do some kind of off-chain key management and like reshuffle key shares every time somebody makes a sale. It would be really great if you could just say everybody signs a Bitcoin transaction, and by holding an ordinal, you're able to make that transaction. We can't do really good order books. Like, all of this comes from the fact that we can't validate the validity of assets for Metaprotocols. So what do we do about this? We're all trying to figure this out. It would be really, really great if we could actually encumber L1 Bitcoin with Metaprotocol rules. Some options that people in the community have been exploring. One of them is you just don't believe anything I just said. You said, you know what, we've got a lot of space for scripts. Bitcoin script, you can add things, you can subtract things. Maybe we can make it work. So this is kind of like the BitVM approach of we're just going to do a really big script, and it'll work anyway. And in fact, what BitVM and all of its derivatives are doing, like BitVMX or different generations of BitVM, what they're trying to do generally is validate a zero-knowledge proof so that they can kind of compress the history of the transactions that they are validating into something that's either constant size or grows logarithmically. Some challenges for sort of large things like BitVM for Metaprotocols, especially things like ordinals, is things like a BitVM bridge is actually an optimistic reimbursement system. So a bridge operator will pay you out first and then pay themselves back from the bridge funds, and the script kind of keeps them honest. That doesn't really work with non-fungibles. And for fungible tokens like runes or something, you're going to have challenges where like the operator still needs liquidity. Covenants are a thing that people say like, oh, well, maybe when we have covenants, we can solve this. We actually did a bunch of work on using OpCat to try to build AMMs for tokens like runes or BRC20s. One of the things that we found is because you have this sort of variable length history problem with runes or BRC20s, even with something like OpCat, you can't really validate token validity on chain. So we did a bunch of work on new token protocols that have constant size proofs of token validity. That's great if you want to buy into that token system, but what ends up being really challenging there is because of things like Bitcoin relay limits and just other policy on Bitcoin, it makes swap markets very difficult. And then there's another option, which I think has been explored a little bit in bridges, but hasn't really been explored very much outside of bridges, that we're going to talk about today, which is policy signers. So, you know, this might solve your problem or it might make it worse, but we're going to talk about it. A policy signer conceptually is very simple. It's a box of logic and maybe some state that takes in a PSBT, applies some logic or some policy, and then can sign the PSBT if it conforms to the policy. So, and what's special, what we're going to talk about today, is that if you hold the Bitcoin signing keys in something like a trusted execution environment or an HSM, then you can actually build trust that this thing is not going to misbehave and that you can actually encumber Bitcoin with it. So conceptually, just think of this as a really, really simple machine. You have unsigned transactions come in, and then the policy signer, the thing that's kind of magic here is that the policy signer can depend on whatever state you want. So if you're trying to build a swap service for runes, maybe you have the ORD database here, and you can actually check if this is a valid rune. If you wanted to build a DAO voting system where everybody with a puppet is allowed to vote on chain about what to do with the money, then maybe you actually keep track of what addresses are valid puppet holders, and then they're the ones who are allowed to sign. So the idea is unsigned PSBT comes in, you run whatever policy logic you want, you can base it on whatever state you want, and we'll see some real world examples at the end. And then if it's conformant to the policy, it returns a signed PSBT. If it's not conformant, it errors. So just a really concrete use case here. Let's say that we wanted to go back to our runes on-chain liquidity example. You could say, I'm going to lock 1 Bitcoin to the pub key of my policy signer. And then anybody can send a PSBT in. Maybe they do it over Nostr. Maybe we aggregate these things together into a marketplace and give you like a Uniswap interface. Maybe you send it via carrier pigeon, whatever. You send a PSBT in that says, here is some units of the foo token. I want to take some of the Bitcoin out. The policy signer can just do the math about whether or not you're paying the right price. And if it is, it signs the transaction. It's a valid Bitcoin transaction, and you've done a swap. And the thing that's really cool about this is that this doesn't require the buyer to like come online and sign a transaction. This is just running on a server somewhere. It happens asynchronously, 24/7. It's not on-chain liquidity. That's why I called the talk faking it really well. It kind of has the same experience as if this was an on-chain smart contract, but it's actually an sort of asynchronous like server signing process. That's great, but I just said you're going to put 1 Bitcoin on hotkeys on a server somewhere and have it automatically signing PSBTs. Like, So how do we actually trust that either if this is my server, that it's not going to be compromised, or if I'm going to run this as a service and you're going to put BTC into it because you want to provide liquidity for some token, how do you know that I'm not going to rug pull you and take all of the money? So there's a bunch of ways that you can kind of formulate these questions, but I think it kind of comes down to how do you know or how do you trust that the signer is only going to sign the allowed transactions, they're not going to go sign other ones, that it's not leaking your keys or misusing them. Leaking could be things like, every time it logs an error, it includes the private key in the error, or it just stores the key improperly, or maybe there's some other policy that's running that says, hey, if Rijndael, sends in a PSBT, then we're just going to give him all the money, right? You want to know kind of what are all of the cases where this thing is going to sign for you. So a tool here that, again, not useful in all cases, but has actually gotten a lot of success in production deployments with real money and real Bitcoin is remote attestation mixed with some key management services. So remote attestation is kind of a family of protocols and tools that let you verify that your code is running unmodified inside of some execution environment. So this could be like the secure enclave on your phone, or a lot of times in servers, it's what's called a trusted execution environment. And the way that this works is when you boot your enclave code, the trusted execution environment measures the code that's running and then signs a hash of that code. So if you imagine that you have your signer policy in GitHub somewhere and you use something that has a deterministic build, you could go and build it from GitHub, like read the code, become comfortable that this thing isn't going to run away with your money, get a hash of this is the code that's on GitHub, and then go verify that this is the code that's running in the server because the hashes match and because you trust the root of trust of that trusted execution environment. And we'll see this in a second. There's all kinds of devices that can do attestation. In all of your laptops right now, there's a thing called a TPM. It's a trusted platform module. This is how you do secure boot. When your machine boots up, it checks a signature on your bootloader and then uses that to go and decrypt your hard drive. So you're actually doing attestation every time you turn your computer on. It's just local. In servers, a lot of times you have a thing called an HSM. There's a hardware security module. This is like a usually 1U rack-mounted appliance that's tamper resistant. If you unscrew the case screws and try to open the case, it wipes all the keys. The actual keys themselves are kept in a module that's filled with epoxy and wrapped in aluminum so you can't drill into it. These are like hardened key management devices. The roots of trust for the internet are inside of HSMs. And then there's been a trend over the last couple years where cloud providers have been offering sort of trusted execution environments that support attestation that you can run in the cloud in things like auto-scaling groups. So the one that I've had the most use, in anger with is AWS Nitro Enclaves. So we're going to talk about that because it's something that you can go and spin up without having to go and spend $30,000 on an HSM. You can play with it, shut it down, and I think it's a useful tool. So is everybody familiar with EC2? You like rent a server in the cloud? Okay, great. Yeah, right. Tidwell's a little iffy. So you rent a VM in the cloud, and the way that this works, right, is AWS has a server with a whole bunch of cores, and they carve it up, and they will rent you cores and memory, and it's a virtual machine. A Nitro Enclave is a sealed VM, so it's running on the same physical hardware as another one of your instances. That's called the parent instance, but it's running on separate CPU cores. It has separate memory, and it has no network access and no disk. So it's just this sealed off, dumb, instance that the only communication it has to the outside world is a single virtual socket to the parent instance. So from your instance, you can send TCP messages over this socket, but otherwise it has no disk, it has no networking. And when it boots, there's a separate piece of hardware in the server called the Nitro Security Module that hashes the contents of that enclave and then provides you a signed attestation document that chains up to a certificate issued by AWS. And then you can hand that signed attestation document to other services, and then you can say, oh, this is the hash of what's running inside. And you have to really trust that, or the trust that you're making is that AWS isn't compromising the security of their highest trusted execution environment to get to your keys, which based on market caps, that's probably a pretty good bet. So what this looks like, going back to our kind of PSBT in, PSBT out model, is you have a client of your service hitting sort of like an API. This is like a web service or some RPC service that you're running. That's the kind of yellow box. Everything inside that box on the right is running kind of on the same hardware, but these two bits, the enclave and the policy signer API, are separate VMs. And so you have kind of the public-facing portion that gets in a request. It makes a PSBT, sends it over this socket to the enclave. The enclave is the bit that's actually holding keys. It signs it and then sends back a signed PSBT. So it's PSBT in, PSBT out, and then the keys never leave. And that's the important part. As long as the keys never leave, you don't have to worry about your signing keys walking away. This presents a little bit of a problem. You want to put this thing in an auto-scaling group. You want to have this thing get replaced if it crashed. You don't want to get paged at 2 o'clock in the morning. How do you get the key into the enclave in the first place? And the answer to that is using a technique called key wrapping, and you combine that with remote attestation, and that lets you automatically get the key into the enclave without you having to go and somehow manually duck punch this thing into the enclave. So the way that this works is same picture. We have our policy signer. We have the enclave. The enclave is able to get attestations from this Nitro security chip. And then we have this key management system, KMS. This is like an AWS service. There's versions in every cloud provider. And this thing is like an API around a bunch of HSMs and similar interface where they will let you use keys, but they don't let you export keys. So you send data in, you say encrypt it or decrypt it using a certain key, and then they send you the ciphertext or the plain text. And what you do is you take your Bitcoin signing key and you wrap that with a key from your KMS, right? So your key is now encrypted by the KMS. And then what you do is when the enclave boots, you go and fetch this wrapped key from your key storage. This could be an S3 bucket, could be a database, whatever. This has to be fetched by the public part, because that's the part that has network access. The enclave cannot talk to the network. So it fetches that, feeds it over the socket to the enclave. The enclave then generates a new key pair. This is like an ephemeral public-private key pair used for encryption. It takes the pub key and sends that to the Nitro security chip and says, hey, give me an attestation of the code that I'm running, but I want you to include my pub key in this attestation document. What happens is the Nitro security module looks, hashes the software that's running in the enclave, and then makes a document that says, this is the hash of the software that's running, here's the pub key that you just gave me, and then signs the whole thing. So the enclave gets back this signed attestation document, and then sends the signed attestation document along with the wrapped key to KMS. KMS looks at the attestation document and says, okay, you're running the code that you're supposed to be running because the hashes match. I'm going to decrypt my key, right? I'm going to unwrap this, and then I'm going to re-encrypt it with the pub key that's in the attestation document. What this lets you do is this lets you send that key back to the enclave, but the public part of your instance can't see it because it's encrypted with the key that was generated by your enclave. So this is a way that you can shuttle this very sensitive signing key across the network and across untrusted network boundaries without anybody seeing it except for the enclave. And now you have your key, you start taking requests. If you implement this model, you can put this in a auto-scaling group. So if you're running like a swap service, you want to do Uniswap for runes, or you want to do some DAO voting thing for your ordinals collection, you can put this in an auto-scaling group, and if all of a sudden you get slammed with traffic, you get the loving hug of the internet, and your fleet has to scale up, instances of this can scale up and walk through this process and provision their own keys, and it's completely hands-off, lights out, and you have assurances that the only things in the network that are able to touch your Bitcoin signing keys are these enclaves because of this attestation. So if you do this, if you actually go down this insane path, what you're going to do is just what we talked about. You need to wrap your signing key with KMS, and then your enclave image creates what are called platform configuration registers, PCRs. These are hashes of the different parts of your software. So there's a hash of the entire thing. There's a hash of just the bootloader. There's a hash of just kind of the OS image. And you can specify policy in KMS to say which hashes have to match, including all of them, in order to use these keys. And again, the way that KMS works is they hold a key for you. You can use it for encryption and decryption, but they never actually export it. So the best practice that I would recommend that we've actually done in production in a past life that I'll talk about in a minute is you take this KMS and you actually stick this in a separate account that has no users, has no running infrastructure. There's like nothing else in there. You just lock that down, and that gives you a decent amount of assurance that the only thing that's allowed to use your KMS decryption keys are this signed enclave code. If you want to actually go try this, we've got a hackathon going overnight and tomorrow, or when you get home, if you want to actually go and kick the tires on this. This sounds really complicated. It's actually surprisingly easy to get something up and running pretty quickly. The way that you deploy software into this Nitro enclave is actually kind of through like an augmented Docker container. So you can write your signing logic in whatever language you want. In the past, I usually use Rust because like Rust Bitcoin is really good for pulling apart Bitcoin transactions and working with them. So you write your enclave code in Rust, Golang, Python, like whatever you like. Hopefully something with a reproducible build. You Dockerize it, and then there's a Nitro CLI tool that will let you turn your Docker image into sort of an enclave image. This is what's called an EIF. And it spits out a bunch of hashes. These are like the hashes of the different layers of your image. And then you take those hashes and you go and load them into KMS, and you say, this key can only be used for decryption if the caller matches these hashes. So anybody else who tries to use that key, KMS will refuse because you don't match the right hashes. And then you deploy it, stick it in an auto-scaling group, and you're done. This might not be the right thing for all users, especially if you're trying to run something where other people are giving you their money. Maybe you want to run multiple signers. Maybe they're in different regions. Maybe they're in different accounts. Maybe they're in different cloud providers. I think another interesting model that, again, has been used for bridging, but less so for kind of one-off applications is that you could have multiple operators that run either different instances of this or run them in different cloud providers, and then they just do a big multisig. And this is a way that you could do completely automated, kind of federated multisig for things where you need to encumber L1 Bitcoin based on Metaprotocol rules. The other thing that you can do that's starting to show up in the wild, like just barely, is you can have clients or other parts of your system actually fetch these attestation reports. So imagine that you build like a mobile app or a mobile interface to enable token trading. You could actually have the mobile app fetch the attestation from the enclave and refuse to do any transactions unless it's talking to known software. This is like really interesting. You get kind of this like nice end-to-end channel with the actual signing code that's running in the cloud. You can also do things like every time the public part of your system talks to the enclave, just log all of the attested hashes, and then if anything ever changes, like alarm and call for an adult very loudly. So, putting this all together, if you wanted to encumber UTXOs with logic that we can't currently express in L1 Bitcoin, a way that you could do that is you go and you write your PSBT checking logic. You can depend on other state. You deploy it into something like an enclave or a TEE or an HSM that provides attestation. And then you just fund the UTXOs for liquidity, and now you're able to do these swaps. A real world example of this. So like I wanted to prove that this is not just, I'm like regurgitating AWS sales material here. There's a actual wallet on the market right now. It's called BitKey. It's from Block. And the way that this wallet works is it's a 2 of 3 multi-sig. So there's 2 devices on the left that a user holds. They have their phone, which has 1 key. They have a little piece of hardware. It looks like a little hexagonal rock. These 2 things are held by the user. And then there's a 3rd key that runs in the cloud. And that key is managed in a Nitro enclave. And it bootstraps using the exact key wrapping technique that I walked through. And they use that key for a bunch of things, mostly around recovery. But one of the places where that key gets used most often is they implement a feature that they call mobile payment limits. So the idea is this is a 2 of 3 multi-sig. So normally you would need your phone plus the rock-looking thing. You tap them together and you can transact. But what you want to be able to do is leave the rock at home in your sock drawer, safe, whatever. So if you're out and about, if you want to be able to transact with just your phone, you can set a limit to say, my phone alone is allowed to send $200 a day in Bitcoin. Now, this is actually a very difficult policy to implement in pure L1 Bitcoin, even if we had whatever covenant you want to design, because wallets are made of lots of UTXOs from different addresses. Keeping track of cumulative spend at the wallet level in a UTXO-based system is just hard to wrap your mind around. So what the BitKey policy signer does is it keeps a state database of, for each kind of unique wallet identifier, here's how much I've signed for today. And so when you send it a PSBT to spend $50, it can look and say, okay, is this $50 spend going to push this wallet over its daily spend limit? If it's not, I'm going to co-sign the PSBT. If it is, I'm going to return an error message, and the user is prompted to go and get their hardware. So this is like an actual deployment of policy signer running in the cloud right now that has customer money on it. And because it's fully automated and lights out, they can scale up and down with demand. If the instance crashes, it gets replaced. And they have good controls so that not even members on the team can get to the keys because of how this remote attestation works. So I think I've got about a minute left. If anybody has any questions, you can find me on Twitter at Route13Maxi. Our GitHub is github.com/TaprootWizards. We don't have very much on there. Like, we don't have very much public GitHub stuff, but we do have a little Rust utility for doing batch ordinal sends. So if you need to send like 500 ordinals to 500 different addresses, we actually have a nice little utility there. So check it out. Thanks for listening.